A kickoff sends a football player with an initial velocity of 25 meters per second at an angle of 50 degrees above the horizontal. The 6 parts to this problem. A. Find the horizontal and vertical components of velocity. B. Find the time it takes for the ball to reach its maximum height. C. Find the maximum height of the ball. D. Find the time it takes for the ball to reach the ground after reaching its maximum height. E. What was the total time the ball spent in the air? F. What was the horizontal distance the ball travels before hitting the ground? Now, to help us visualize this problem, I have drawn a picture of a football player and a football. When they kick the ball, it follows a parabolic arc. It starts off on the ground, they kick it, it moves up to its maximum height, and then it comes back down to the ground. To help orient where the object is going to be in relation to some reference point, I'm saying my reference point will be the initial position of the ball. It starts off on the ground at, the way I'm defining it, its leftmost point horizontally. So this will be our coordinate, 0 meters horizontally and 0 meters vertically. Defining it in that way will allow us to easily populate a list of horizontal and vertical variables to try to solve all 6 of these parts of this problem. So for part A, we're trying to find the horizontal and vertical components of velocity. Once we do, we can add that to our list of variables. So we have our initial velocity of 25 meters per second. It is at an angle 50 degrees above the horizontal. So essentially, I've taken that same x, y coordinate plane that I drew in my picture, and I just had my initial velocity vector originate at the origin, where the ball would have been. This is indeed our initial velocity, but we need to figure out how much of that 25 meters per second causes the ball to move right and how much of it causes it to move up. This is where we're going to need to use trigonometry to figure out the x-axis component of velocity and the y-axis component of velocity, because there will be some amount of initial velocity horizontally and some amount vertically. To figure out the horizontal component, we're going to use the cosine function. Cosine of our angle is equal to the length of the adjacent side of the triangle to that angle divided by the length of the hypotenuse. Writing that in the way that makes sense for this problem, cosine of our angle is equal to our initial velocity horizontally divided by our initial velocity. Rearranging that to get our initial velocity horizontally by itself would require us to multiply both sides by v0 and then plug in our values. 25 meters per second for v0 and then 50 degrees for theta. So our horizontal initial velocity would be 16.1 meters per second. To do the same thing with the vertical component of velocity, we're going to use our sine function. Sine of our angle is equal to the length of the opposite side of the triangle to that angle divided by the length of the hypotenuse. Or in this case, sine theta is equal to v0y divided by v0. We can multiply both sides by v0 to get v0y by itself and plug in our 25 meters per second for v0 and 50 degrees for theta. So our vertical component of the initial velocity would be 19.2 meters per second. Now that we have this, we can start populating our list of variables. We have previously defined our starting position of the ball as a horizontal position of 0 meters. We don't know where its final position is going to be. That's actually what we're solving for in part F. But we do know its initial horizontal velocity is 16.1 meters per second. And because this ball is behaving like a projectile, we also know that that would be its final horizontal velocity, because for projectile motion, the horizontal acceleration would be 0. For our vertical variables, the ball starts off at a height of 0 meters. It ends at a height of 0 meters. It starts off with an initial vertical velocity of 19.2 meters per second. We don't know what the final vertical velocity would be, but we do know that while it's behaving like a projectile, the acceleration should be negative 9.8 meters per second squared. And then the thing that connects the horizontal to the vertical variables would be our time. To figure out the amount of time it takes to reach its maximum height, it might be useful to actually break up our vertical variables into two parts. The vertical variables while the ball is moving up to its maximum height, and then the vertical variables while it's moving down. Because really, here is where the ball would be at its maximum height. That looks like it's about the halfway point. It moves up, and then it moves down. We wouldn't necessarily have enough information previously to solve for the time it takes to reach its maximum height if we were to just focus on the up and down motion as a single continuous motion rather than breaking up into these two parts. Because this way we can say that the starting position is still 0 meters, just like it was in the previous step. But now we don't know what its final position is. That would be its final vertical position while it is moving up, or its maximum height here. We know its starting vertical velocity would be 19.2 meters per second. And now we actually do know the final velocity. Because at the point where the ball can no longer go any more up, once it reaches its maximum height, that is where the ball has a velocity of 0 meters per second vertically, while it's still accelerating downwards at a rate of 9.8 meters per second squared. Now, just to finish up our list of vertical variables, we don't know what that starting position on its way down would be. That, too, would be the maximum height. We know that its final height would be 0, though. It'd be back on the ground. We know that it would start off with an initial velocity of 0 meters per second at its maximum height. We don't know what the final velocity would be, but we do know its acceleration is negative 9.8 meters per second squared. And we still don't know the time, but that's what we're solving for. We can solve for the time rather quickly using this equation, if we're just focusing on the vertical variables while the ball is moving up. Because we know the final velocity, we know the acceleration, we're looking for the time, and we know the initial velocity. Plugging in the values we know, 0 for the final velocity, negative 9.8 for the acceleration, and 19.2 for the initial velocity, we can simplify and rearrange the equation to try to get time by itself. Our time would be 1.96 seconds. That is the amount of time it would take from the time the ball has been kicked to the time it reaches its maximum height. That allows us to say that the time it takes to go up is 1.96 seconds. That can be a new variable we add. However, at this point, t is not the same for horizontal, up, and down. We're going to need to figure out what those times will be later on in order to answer parts D, E, and F. But right now, we're just trying to figure out for part C what the height is, what the maximum height will be, using the time it took to go from the ground to its maximum height. There are a couple of ways that we could go through this. One way is we could use an equation that includes time with it. Or alternatively, we can use the v-squared equation, one that does not necessarily need the time in it. Because if we use the v-squared equals 2 times our acceleration times our displacement plus our starting velocity squared equation, we could have skipped part B and figured out exactly what the height would have been. So we're just going to continue with this approach. Our final vertical velocity while it was moving up would be 0. Its acceleration, negative 9.8. Its change in position, its displacement, would be the final position minus the initial. And then the initial velocity would be 19.2. We square the final velocity, so 0 squared is 0, and then the units get squared as well. We did the same thing with the initial velocity of 19.2. The value and the units got squared. And we put in 0 meters for our initial position. Simplifying that down and rearranging the equation ever so slightly allowed us to subtract that negative 368.64 meters squared per second squared from both sides and set that equal to 19.6 meters per second squared. That's 2 times the acceleration times the final position. We can divide both sides by the negative 19.6 meters per second squared, which would give us a value of 18.8 meters as the vertical position once the ball is at its maximum height. We could get that same answer by using our equation that was the y position is equal to the initial y position plus our initial vertical velocity times time plus 1/2 times our acceleration times time squared. We had all of those variables. We'd just be using the 1.96 seconds there for our time. Just another way for us to solve the exact same answer. But right now, we also want to figure out the amount of time it takes for the ball to return to the ground after it reaches its maximum height. This is where we can use that equation that I was saying was an alternative approach to figure out the ball's maximum position in the previous step. Plug in the variables we know. Remember, right here, this is just where we're using the vertical down list of variables. The final position would be the height of the ground, 0 meters. The initial position would be the maximum height that we solved for in the previous step, 18.8 meters. The starting velocity is the velocity of the ball when it was at its maximum height, 0 meters per second, times t, the thing we're solving for, plus 1/2 times our acceleration of negative 9.8 meters per second squared. That stays the same while the ball is a projectile, times time squared. We can subtract the 18.8 meters from both sides and simplify down the rest of the rightward term. Divide both sides by the negative 4.9, which would give us 3.84 with units of seconds squared. That's equal to time squared. Take the square root of both sides, and then the time it takes for the ball to return to the ground is 1.96 seconds. That is the total time the ball was spent in the air. Time total is equal to the time going up plus the time going down. It's the same amount of time to go up as it is to go back down. So our total amount of time would be 1.96 seconds plus 1.96 seconds, which is 3.92 seconds. Another way that we could have solved for the amount of time it took to return to the ground, instead of using that full kinematic, we could just use an understanding of parabolas and the assumption that as long as we just have a single continuous and uniform acceleration that entire time, 1/2 of the parabola would be equal to the other half of the parabola. So we can use symmetry to have answered a few of those previous problems. A big thing is the amount of time it takes to get from one height to the maximum height will be the same amount of time it takes to go from the maximum height to that height of 0. But this is how we can figure out our total time. Just add up the two parts. Once again, had we chosen not to figure out the individual parts, we still could have figured out the total time. That's going back to that original list of vertical variables that we had populated back in part A. We can figure out time using the same equation we used to figure out the time for the second half of the ball's journey. Both the final and initial position would be 0 meters. The initial velocity would be positive 19.2 meters per second. The acceleration is negative 9.8 meters per second squared. Simplifying the terms and factoring out one of the t's would allow us to figure out what 2 times the ball is at a height of 0 meters. Now, 1 time is obviously a time of 0 seconds. That was the initial time. That would be the time when this t right here is 0 seconds, because 0 times this entire term would equal 0. The other time is at a time of 3.92 seconds, where 3.92 for this t times negative 4.9. When added to 19.2 would cause this entire term here in parentheses to go to 0, which would allow us to have 0 times this other t equals 0. Just another way of figuring out the same answer for part E. And then finally, now that we have the total flight time of the ball, we can finally figure out how far horizontally the ball would have traveled. We can take the equation that allows us to figure out the final position of the object. Plug in the values that we know. 0 meters for its starting position, 16.1 meters per second for its starting horizontal velocity, 3.92 for the seconds, 0 for the horizontal acceleration, and then 3.92 for the final time, to solve for how far the ball would have traveled. Ultimately, the ball would have traveled horizontally a total distance of 63.12 meters.